All right, so we're working up to the point to be able to completely interpret the infrared spectrum of methane. And what we did previously is we showed that there are four different normal modes, okay? Um, well, four different normal modes with different symmetries, actually a total of 9 because of degeneracy. But those were A1 plus E plus 2T2 modes. And we could look at the character table and from all of our rules know that only the ones with symmetries of the transition moment operator are going to be IR active. So the transition moment operator for IR spectroscopy is X, Y, and Z. And these vectors happen to all be triply degenerate and transform together as the T2 symmetry in the TED point group. And so what this left us with is that the two T2 modes, one of those, remember we said was a bend, one of them was a stretch. And in the last video, I showed you how to figure out which ones are bends and which ones are stretches. But those two T2 modes are going to be IR active. A1 and E modes, those don't transform as X, Y, or Z. And so those are going to be silent. So based on this very simple picture, we would expect that we would have two peaks in the IR spectrum for methane because, well, there's two T2 modes that are IR active, okay? And yes, we went on and talked about which ones were bends and which ones were stretches. If you look at the IR spectrum, this logic is wrong. It's incomplete, as it turns out. The experimental IR spectrum, and we'll go over it later, has 4 peaks, not 2. The reason for this is only 2 of the peaks are due to fundamental modes. Remember we said that normal modes or fundamental modes are like the strings on a stringed instrument, like a guitar or a ukulele or something, right? And so there are other things that can happen with modes modes can combine, like you're playing 2 strings at once, or you can play an overtone where you're going to put your finger on one portion of the string to change its energy, right? Change the path length of the string, and it makes the string play at a higher frequency. So you can get peaks other than those due to fundamental modes from either what are called combination modes, that's like 2 strings, or the overtones of the fundamental normal modes. All right, but just like fundamental normal modes, the symmetry has to be correct of the overtones for them to be IR active. Just the same thing as before. You have some intensity integral where the intensity is proportional, and this time we're talking about an overtone. It's going to be proportional to psi initial times the transition moment operator times psi final d tau. And the only thing different about this expression compared to the expression for fundamentals is this nu part here. We're going to take psi final and raise it to the power of nu. And what is nu? Nu is that harmonic oscillator I drew earlier, where that's nu equals 0 is the ground vibrational state. Okay, there's no vibrations there. That's always a totally symmetric state. So psi initial is always totally symmetric. But the overtone mode could be mu equals 2. That would be like a double overtone. You can have mu equals 3, mu equals 4. Those can be symmetry allowed, but under most circumstances, those are just really rare events. So the integral might be non-zero, but actually more to the point is that this energy gets so high that on a typical IR spectrum, you're not going to see it. And also the intensity will be low. So just because something's symmetry allowed doesn't necessarily mean you will see it, right? Because the intensity could be low for other reasons. But normally when we're talking about an overtone, we're talking about going from the ground state, nu equals 0, to nu equals 2. And so that's what this says here. And where is that going to appear? That's going to appear at about twice the wave number as the fundamental. Because to first order approximation, this harmonic oscillator can be approximated as a parabola, the well of this Morse potential where does this come from? This comes from the Morse potential, right? It's how far apart atoms are. If you put them too close together, you have nuclear repulsion. That causes this to go up. If you expand the radius too much, then there's not the attractive forces of the electron clouds, i.e. the bond, right? So this Morse potential has, you know, a strict physical underpinning. So anyway, this 0 to 2 is going to be approximately equal to twice the wave number or energy as from 0 to 1, the fundamental, okay? And yeah, the higher overtones are usually too weak to observe. That's like 0 to 3 or 0 to 4, and or they're off the experimental IR spectrum because they're too high energy. So let's look at the overtone for of methane. So here are normal modes. That's where we start. And there were A1, E, and 2 T2s. And if we look at the character table, remember that X, Y, and Z, the transition moment operator, mu, is X, Y, and Z. X, Y, or Z. Here they happen to transform all together as T2 and TD. And so what you're going to do here is you're just going to evaluate every possible overtone and see if it is symmetry allowed or not. And so the first one would be the A1 overtone, right? And so, okay, is the A1 overtone active? Well, psi initial always has the symmetry of the totally symmetric state. That's A1, that's the ground state. One's across the board. The ground state isn't excited, so everything's relaxed, so it's totally symmetric with respect to any movement. Then you have the transition moment operator, that is T2, I just said that, so we plug that in here. And then we have the final state, and the final state is where we're going to, and we're asking about the A1 overtone. So that's gonna be symmetry A1, so we're asking about the A1 overtone, so A1 squared. So we know that A1 times anything is just itself, and so we have, you know, essentially A1 cubed here. A1 cubed is a bunch of ones, A1 cubed is equal to A1, and A1 times T2 is equal to T2. So very quickly, we'll get that the symmetry of this product will have a symmetry of T2. Now from our product rules, knowing that only when you multiply something by itself, that's the only time that you'll have something that has A1. So there's no A1 in here in T2, right? And so this is going to be inactive. Let's try the E overtone. So again, the initial state is A1. You know, we're timesing it by 1. You could really drop this A1. You know, if you wanted to, you could drop this A1, right? Because we know A1 doesn't do anything. So this can go away in this formula, right? To simplify it a bit, just like we simplified it before when we were dealing with fundamentals. And so now you have T2. Again, you have T2 because that's what the transition moment operator mu is for IR spectroscopy. As we'll learn in a bit, it's different for Raman spectroscopy. And then you have E squared because you're evaluating the E overtone. You're asking the question, is the E overtone active or could it be? So for E squared, you're going to have to calculate this out or look this up, right? But E squared is going to reduce to A1 plus A2 plus E. And now your integral has a symmetry of this, T2 times A1 plus A2 plus E. You could evaluate this out if you really wanted to. You could factor this out, but you don't have to. And that's because you can tell right away this is not going to contain an A1. The only way you're going to have an A1 is if you have one of these products, right? There's 3 products here, T2 plus A1, T2 times A2, and T2 times E. None of those are T2 times T2. None of those are something times itself. And because none of those are something times itself, none of those will have A1 by our product rules. And so since there's no A1, this is going to be inactive. Lastly, let's do the T2s. So again, we have this initial A1 from psi initial. We can just get rid of that because that's just timesing something by 1. We have T2, the transition moment operator. And then we have T2 squared because we're evaluating the T2 overtone. So T2 squared, you'll have to go through and do this math. That ends up being A1 plus E plus T1 plus T2. If you're not clear on how to do that math, go back to the product table section at the end of chapter 2. Okay, but so you're going to end up with, so that was t squared. That stuff in parentheses is right here. Okay, that's t squared. And all that's going to be multiplied by this t2 right there. Okay, and so do any of these products have something times by themselves? Yes, the very last one is t2 times t2. I don't know what t2 times t2 is. Well, actually I do. No, it's a1 plus e plus t1 plus t2. But even if I didn't know that, I know that something times itself is going to have a1. There's a1, right? And so therefore this integral has a 1, and so therefore this overtone is symmetry allowed by our selection rules. So both the T2 overtones are going to be symmetry allowed.